So good afternoon, everyone. My name is Vinod Menon, and I'm from City College of New York. I'd like to firstly acknowledge my funding sources, Army, Air Force, Army, National Science Foundation, and the Brookhaven National Labs, where some of this work was done. And of course, none of the things that I'm going to talk about would be possible without my students and postdocs, and also in this particular program, my collaborators are Puyan Gayemi, Professor Stefan Kenna-Cohen, and Professor Yishane Lee, who provided the materials. So I'm going to do a quick introduction to excitons. I don't really need to do this here to this audience, but just want to make a distinction between 1A excitons, which is what most of us deal with in inorganic semiconductors, and Frenkel excitons, where the electron and the hole, if you may think about in that language, sits at the same molecular site. So, and the distinctions between the two are, when you talk about 1A excitons, they have a large Bohr radius. They have small binding energies, with the material like zinc oxide having the highest binding energy of about 60 milli-electron volt. They have, because of this delocalized nature of the exciton, they have long-range transport. Condensation has been shown in polariton systems, lasing, and they also have small saturation densities. So these are some of the advantages of, or the properties of 1A excitons. Frenkel excitons, on the other hand, they are highly localized at the molecular site. They have very large binding energies, on the order of an eV. The transport is hopping transport. There's the Forster or Dexter energy transfer. Polariton lasing has been shown at room temperature in these systems, and they have large saturation densities because you can keep pumping harder and harder, and you never fill up the states. So, and this brings me to TMD. So I had, if you look at these two material systems, you see that there are advantages to both of them, and there have been a lot of theory papers on how, if you can actually combine the two systems and realize polaritons, there might be benefits. Well, this is where transition metal Di-Chalcogenides come into play. So the material systems that I'm going to talk about today are moly disulfide and tungsten disulfide. And these materials occur in bulk form in crystals. In fact, you can buy them in an automobile parts store as a can, because they are van der Waals materials and they're good lubricants. And they are similar to graphene. They can be exfoliated because each of these layers are held together by van der Waals force. But unlike graphene, it's not one sheet of carbon atoms. It's actually molybdenum atom with sulfur atoms on either side. Now, if you look at the structure here, if you look from the top, it forms a honeycomb lattice. But on the honeycomb lattice, the molybdenum and the sulfur atoms are located at the two different points. And one take-home message here is, unlike graphene here, the inversion symmetry is broken. And we'll see how that plays a role here. So the question comes, what is the binding energy of these materials? So one of the interesting things about this system is, in its bulk form, they are indirect bandgap materials. And if you keep exfoliating the layers and you get down to the monolayer limit, and it starts emitting light because you become a direct bandgap. However, the direct bandgap happens not at the gamma point, like it happens in most inorganic semiconductors. It happens at the K and K prime points. And so this is in the momentum space representation of the exciton, and this is in real space. So this is one of the excitons in a material which was computed. And you would see that the Bohr radius is about 1 nanometer. So it's much smaller than what is in gallium arsenide, but it's still bigger than what is in a typical organic semiconductor. So it is, to some extent, delocalized. So the question is it really the best of the both worlds? I mean, are we getting the best of organic and inorganic systems somehow in these TMD materials? Well, there are some other interesting aspects. If you look at its binding energy, they have very large binding energy, and that has got to do with the way the states occur in these materials, but also the screening plays a crucial role. So there is strong screening in the layer, whereas it's weakly screened outside. And this means that I can start thinking about playing tricks with the dielectric environment surrounding this 2D material to modify the binding energy or the band gap. And in fact, there is some recent work where people have shown that just by putting small pieces of graphene underneath certain regions, you can modify the band gap of the molybdenum of this 2D material sitting on top. So there is there's an added advantage here. The other aspect of these 2D materials is, because these are 2D, the electric dipoles are all lying in the plane. And this is actually, this is simulation, and this is experimental data where we've looked at the luminescence coming from the 2D material in the Fourier plane. So we just project the back plane of the microscope objective onto onto a CCD camera, and you see that it agrees very well with the emission radiation pattern of a dipole that's lying in the plane, in this case along this plane, and here in this orientation. So they're all lying in the plane, and that has some advantages and disadvantages. We'll see as we go along. The other big advantage of 2D materials that I see is the large oscillator strength. And so this is a graph I've taken out of this paper, and that's your solar flux, because this paper was written with solar cells in mind. But what I like to focus on are these red and blue and green lines, and you can see that at certain energies corresponding to the exciton resonances, you can get up to 10 to 15% absorption of light. Just to put things in perspective, gallium arsenide and silicon, you would need about 15 to 20 times that thickness of this monolayer to get the same amount of absorption. So why is this absorption coming about? There is a lot of discussion on this. However, the current consensus is that it's the D states that are taking part in this optical transition that is responsible for this large oscillator strength, combined with this screening effect that I was telling you earlier. So these two things play a role in this really large absorption of light. And this black line, by the way, is the graphene's 2.5% absorption that you see. So at certain resonances, you can get extremely large absorption of light in these materials compared to standard inorganic semiconductors. Then, of course, they also have, at room temperature, the radiative lifetime is, so this is really the radiative lifetime, and the short lifetime is mostly non-radiative. And this is not a property of the material itself, it's just that the materials are not clean enough yet. However, if you go down to low temperature, you can actually get very fast lifetime, which is actually radiative. And then these long lifetimes you see are these bound localized excitons coming about because of defects in the lattice. So I think I've described why, what might be the advantages of trying to play with these TMDs in cavity polaritons. We had an excellent pedagogical lectures from Jacqueline yesterday, and the day before, and the day before that. And so I don't need to give much of an introduction here, but essentially the idea is that you have an exciton sitting inside a mirror, and you use your in-plane direction as your way to probe the dispersion of this system, and the region of the anti-crossing between the cavity photon and the exciton is the Rabi splitting in this system. And so there's been a lot of work on the systems. I don't need to go into it in great detail. The excitonic component giving the electronic response, scattering and nonlinearity, whereas the photonic component giving the small mass, coherence, and long propagation lengths. It's been studied. Condensation has been realized. Spin switching has been realized in different groups. And I'm just going to have a whole list here of different work that has gone on. So condensation, superfluidity, thermalization of polaritons very recently, 2-deg polaritons, where they've combined a 2-deg in gallium arsenide in one case, in both cases to and realized polaritons, intersub-band transitions, polariton lattices, we heard a lot about it yesterday from Jacqueline, and confined polaritons also from Jacqueline's group, and then most recently some Mark Zender and Sagnac interferometers. So a lot of beautiful work coming out of the standard 3.5 semiconductor materials, with the caveat that all of that is happening at cryogenic temperatures. Now, the TMDs bring you the advantage that the binding energies are 0.3 to 0.5 eV, which means I can start thinking about these things at room temperature. But before we jump into the 2D materials, I should point out that there are other material systems where such strong coupling has been realized at room temperature. Organic materials, whole bunch. There's a whole lot of literature on that. There's hybrid materials where organic and inorganic materials have been studied. There's zinc oxide, which has been studied at great length and was touted to be a great material. However, the problem there is it's all happening in the UV, and that makes it not the most accessible material to do some applications. And then there's gallium nitride, and then most recently there is 2D materials. And there's again already a whole bunch of groups that have shown strong coupling. Now, you might ask, okay, so what? another material list on this whole list of things. So I have TMD materials. What does it bring to me? Well, this is what I struggled with the first paper that we wrote. How do I make a case for the fact that this 2D realizing polaritons in 2D materials is any better than in organic or in zinc oxide materials? Well, there are some advantages. And so here I do a comparison, one-to-one comparison between TMDs and gallium arsenide quantum melts. So you can see the big advantages of the binding energies. The mobilities are not anywhere as close as gallium arsenide. They're in around 400 centimeters per volt second, but it's much better than what is in organic materials. And in organic materials, you have so much disorder. So compared to that, you're actually in a better state with this TMDs. So we went ahead and did some experiments right away. So we took these, in the first set of experiments, we took moly disulfide that was grown by Yizhen Li's group. And these are CVD grown, so that's why you see these large triangular flakes. And this is the differential reflectivity showing the two excitonic resonances. And this is the absorption, the PL photoluminescence of this material showing the photoluminescence coming from this exciton A. So, and then there is I'm not going to go into the techniques of this, but there's a way to transfer these materials from the as-grown sample onto the cavities. But if anybody is interested, I can discuss that offline. Needless to say, you can actually take a conventional DBR cavity grown by something like chemical vapor deposition, and then transfer this monolayer of this material in there, and then grow your top layer on top of the top mirror on top of that. Now, because these monolayers are not there everywhere inside the cavity, you can go and probe different regions. And so this is a region where there is no monolayer material sitting inside. You get the reflection from the bare cavity. So that's your bare cavity resonance. And then you go into the region where the 2D material is sitting, and you see the split modes. Well, split modes is not always a signature that there is strong coupling. It could be due to various other reasons. However, you need to see anti-crossing. So this was our first experiments where we were trying to do this anti-crossing and seeing if there is anti-crossing. So we do see these modes. In fact, if you zoom in, you will see the two modes inside the system, and they do show anti-crossing. And in fact, you can fit that to a simple coupled oscillator model and establish that there is an excitonic component here, it's more photon-like, and also establish the condition for strong coupling. I must say that this first demonstration, we were barely at the threshold of strong coupling because of, if you look at this condition, that has to be satisfied. However, we do see the anti-crossing behavior, and that was our first paper on this work. We also showed this in photoluminescence, where we see this anti-crossing behavior and with similar Rabi splitting of about 46 milli-electron volt. Now there's been a whole set of other people who have shown strong coupling at room temperature and at low temperature from these materials. But never, I don't have to go into the details of all the work, but everyone sees strong coupling. The low temperature, the data looks much cleaner, obviously because the line widths are much more narrower. And so one of the things I want to point out here is, unlike in inorganic semiconductors where in typical gallium arsenide-based systems where the cavity Q is pretty high, in these systems, because the inherent line width was so broad at room temperature, which was about 30 milli-electron volt or so, we did not actually need to build a very high Q cavity. We could get away with a crappy cavity and still be able to see anti-crossing in this system. So this was the first work, and we showed the anti-crossing behavior. But really the question comes, what does TMDs bring to the polariton community that normally you don't get out of these other systems? So this is where I want to discuss valley polarization. We heard a little bit of that in the morning from Guido on how you have this valley polarization in silicon. Well, in this case, in the TMDs, because the K and K prime points are not similar, and because you've broken the inversion symmetry in the system, the K and K prime points, which are the points where you have the direct band gap, they have spin selections which are exact opposite. So in other words, I can shine light with right circularly polarized light and excite the K valley. And if I shine light with left circularly polarized light, I excite the K prime valley. And so this is the idea that you can use an external light beam. And so this is the original paper, one of the original papers where you are exciting with sigma plus, and the light that comes out is mostly sigma plus with a little bit of sigma minus. And if I shine with sigma minus, it's mostly sigma minus with a little bit of sigma plus. And the reason you're getting a little bit of sigma, the opposite helicity in this case, is because there is things like inter-valley scattering, which doesn't, so hence you don't get all the transition happening at the same valley. So, and then you often define the helicity as the ratio of the intensity of sigma plus minus sigma minus divided by sigma plus plus sigma minus. So that's how you define the helicity. So the experiment that I'm going to talk to you now is essentially looking at the valley polarization properties of the polaritons itself. And the experiment is as follows. So this is your upper branch, this is your lower branch, this is your cavity mode, that's your exciton. And what we want to do is the following. We want to do two experiments. The first experiment, I will pump the exciton reservoir. So that's right here. I'm going to pump the exciton reservoir directly and look at the emission that is coming close to k equal to 0. So in other words, I'm asking the question, if I pump the exciton reservoir, will the polariton emission happening at k equal to 0 have any fingerprint of the helicity or the valley of the valley property of the exciton that is being excited? That's experiment 1. The experiment 2, I'm going to pump below the exciton reservoir, so in the band gap, but at the polariton state itself. And then I'm asking the question, will the polariton emission still have the property of the exciton reservoir? So if the polariton state is formed instantaneously as soon as it's inside the cavity, just the fact that it's inside a cavity, then it shouldn't matter whether I pump there or here, I should still get the polariton emission to show valley polarization. And that was the hypothesis that we went with. So in fact, we went to a much simpler cavity. This is just a silver mirror sitting with silicon dioxide and silver, and we transferred this monolayer material. We went from the CVD grown large flakes to Scotch tape exfoliated samples, simply because they were much more brighter and easier to work with. And this is a Fourier space image of reflection and photoluminescence from this sample for samples with different detuning. So the detuning meaning this difference in energy between at k equal to 0 between the exciton and the cavity photon. And you see that all three of them you can extract out the anti-crossings and the Rabi splittings. So the photoluminescence is all happening in the lower branch. You see the typical bottleneck effect on those edges, especially in these large detuned cavities. And then at the lowest detuned cavity, actually a positive detuned cavity, most of the emission is coming from the bottom branch. So this is just to prove that we are once again, even in these really simple metal cavities, we are getting strong coupling in the system. And this is again at room temperature. But now we do the experiment where we do the pump 1 experiment where we are resonant with the exciton energy. So we are coming with sigma plus excitation and at the energy corresponding. So this is the resonant excitation. We are exciting exactly at the exciton reservoir. And then we are looking at what is the photoluminescence that is coming out close to k equal to 0 from this system. And you see that most of the, there is a difference in the emission intensity that is coming from sigma plus versus sigma minus. And it's exactly reversed. When I pump with sigma plus excitation, I get mostly sigma plus and lesser of sigma minus. So I'm seeing this valley polarization property. But what is interesting in a cavity system is there is also, as you go from k equal to 0, you're changing the fraction of the exciton in that polariton branch. So there has to be a dependence of the helicity on k parallel or the in-plane wave vector. So that's what is shown here, that as I go from k equal to 0 to larger values, for the one sample that is close to resonance or the plus 16 millielectron volt detuning, I see my helicity going up, whereas the other two, it almost stays flat. And I'll come to the reason for why this might be the case. So there are multiple competing effects due to which this helicity is lost inside these samples. Well, or the valley polarization is lost. I alluded to one of them, and that was the inter-valley scattering. Well, in a cavity system, you also have another effect, which is the TE-TM splitting inside the cavity. The TE-TM splitting also destroys valley polarization inside these systems, and hence at larger values of k, you're going to get lesser and lesser of this helicity being restored. So especially for the large detuned cavity, which is very photon-like, this TE-TM splitting actually dominates over the other effect, and hence we lose some of the helicity. Nevertheless, you're getting about 16 to 20% helicity inside these samples, which is comparable to what happens in bare materials. The second experiment we wanted to do was to go below the exciton reservoir. So we are pumping in the band gap at the polariton branch directly and asking the question if the emission coming at k equal to 0 is going to be show valley polarization. So again, the same experiment. So we are pumping resonant at 1.95 eV in this case, which corresponds to the lower polariton branch. So just to show you this. In this particular experiment, we are pumping right here somewhere. It's about 1.95 eV. And then we are looking at the emission that is coming out here at k equal to 0. So again, we see about 12 to 15% helicity for both the cases. So this is sigma plus pump, this is sigma minus pump, and once again we show that even though we are pumping below the, even though we are pumping directly the polariton state, the emission that comes out of this polariton state has a fingerprint of the valley origin of the exciton that is forming this polariton state itself. So, and this is the theory work that was done by our collaborators, where this is where we show where we expect the maximas in the emission intensity itself. And this is the trend for what happens to why the helicity has a dependence on in-plane wave vector. And we were able to nicely reproduce what happens at plus 16 MeV. However, these two, the error bars that we're getting at the large angles does not really reproduce this. However, it seems like we have captured the basic physics, which is that you have the intervalley scattering and the exchange interaction that happens in these systems between, as well as the TE-TM splitting that happens in the cavities are responsible for why we are losing this helicity. So I must say that we are not the only ones who have done this. There are 3 papers that have come out in the last 2 weeks on this topic from different groups. This is from Northwestern group, this is from the Sheffield group, and this is our work itself. So a lot of interest in this, and my question is, where do we want to go with this? So one of the advantages of these TMDs is they also show trions. And the trions are charged, so it's an electron-hole pair with an extra electron or a hole. So they're charged, which means that now you can use electrical field to control their transport. So this is a setup that we use. I must say that there is some discussions in the community on the semantics, whether it's a trion polariton or is it a polaron. I'm not going to go into that. All I'm saying is it's a charged state coupled to an exciton that I'm going to try and couple to a photon, and then ask the question whether I can actually do some, make these polariton states move, even though they're not above condensation. So what we have here is the structure that we use. It's a boron nitride. We have our contacts going around, the TMD sitting here, the cavity, and then we are applying it's a transistor, so you just apply a gate bias, and we want to see if we can move it. So this is work in progress. We've made the devices. The first experiments we've done is just to show that we can actually do a gate voltage control and start exciting the trion mode. We have not seen the strong coupling between the trion and the exciton and the cavity photon yet. But I do think this is one area where the TMDs actually bring in, because even the trions are supposed to have binding energies on the order of 30 milli-electron-volt, which means we can, it might not be at room temperature, but we could probably pull this off at liquid nitrogen temperatures to do some experiments. So that's one outlook, and this is the most futuristic of that. So this is about whether you can do condensation at room temperature. And this is a theory graph from this particular paper. The reason I put this up is, at least as per their calculations and also a few other groups, the numbers that are needed to realize strong coupling at room temperature is not far out. In fact, if you have reasonable quality material, if you can get better quality material from what is right now, you should be able to get to this number. Current estimates, we are somewhere in this number of about 10 to the 9 to 10 to the 10th, but I do believe that we should be able to push it to that limit once we get the material. So right now, one of the biggest stumbling blocks in this field of 2D material-based exciton physics or exciton polariton physics is the quality of the materials. And just recently, at least 2 groups have shown that at least at low temperature, they're getting line widths that are lifetime limited. So down to about a 2 milli-electron-volt or so. So, but that's at low temperature. So with that, I want to switch gears and move to something else. So if there's any question on this topic, I'd be happy to answer. Yes. The excitons are, for at least for the K vectors that we're interested in, it's almost flat. It starts folding, bending up much farther out. So remember, the light line is much more steeper, so this is farther out. Oh, because, yeah, you can just look at the absorption of the state, do a separate absorption, not in the cavity, but outside the cavity, and then, yeah. Yes. Yes. Absolutely. Yes. Well, it's a question of the timing. So how long does the polariton state versus how much precision you have of the state. Exactly. So it helps. So once again, the poor cavity came to our rescue. We don't think we have got to that regime yet. We need to pump harder. Yes, we don't think we have seen any. We have not seen till date in any of our samples. Even we have tried pumping harder, we have not seen anything nonlinear. Yeah, so we see the blobs on the two sides, and we've tried pumping there, but nothing. But we're doing some low temperature experiments now to see if we can get it. Yeah. How many of them are you creating? Well, it's a yeah. Oh, so the binding energy is 50 MeV. No, sorry, 0.5 eV compared to yeah. So okay, if there are no other questions, then I'll move on. So I'm going to ask. So this is another problem with 2D materials, which is that there's all the hype about 2D materials that they're of course they followed from graphene, so everyone's interested in it and everything. And they also, when you go to the monolayer limit, you get a large increase in intensity. In fact, it's about three orders of magnitude increase compared to two-layer material. But if you ask the question, what is the actual quantum yield of this material? Or in other words, if I put 100 photons, how many photons do I get out of the system? It's pretty bad. It's actually 10 to the minus 3. So it's a very poor emitter, despite the fact that there is such a large oscillator strength. So this comes about the fact that the material has poor quality and there's a lot of defects in it, and so on. And there have been various approaches to improve this. Of course, one is the cavity. You can put it inside a cavity and increase your spontaneous emission rate. So people have done it with photonic crystal cavities, external cavities, and so on. People have done it with plasmonic structures of various kinds. And there have also been a lot of reports of so-called lasing in these systems. But again, it's coupling to these cavity modes, and they've shown sharp modes in the system. People have done chemical treatment of these materials and done it. Well, the chemical approach is good, but it doesn't seem to survive too long. So the question that we asked is there another approach, a photonic approach we can take to improve the spontaneous emission over a broad spectral range? And I'm going to, since there's a lot of people with interest in Cavity-QED, I want to introduce a new platform where I think you can do some interesting Cavity-QED. And that is, and to introduce that, I want to introduce some basic optics. So this is an anisotropic material. So it's typical Born and Wolf material. So you have you have a block which is anisotropic, and if this anisotropic material is formed out of two materials A and B, where this A and B are materials which are extremely thin, where the light doesn't see these individual layers, then it essentially acts like an anisotropic material like calcite or anything like that. And if you have that, you can define a dielectric constant of this material perpendicular and parallel to the layers. And this is just your Kirchhoff's laws. You get your Fa being the fill fraction, or the ratio of the material A to material B. And you get this standard thing, and if you plot your constant frequency surface, in this case, it's an ellipse. And in the case of an isotropic medium like air, it's a sphere. And so you have the equation of an ellipse in this case. So good. However, if I made one of my materials metal, or something with a negative epsilon, then what happens is, so say I take my B to be negative, and my epsilon B is negative, so it's a metal. And if I control the amount of fill fraction of the metal in there, then I can make this number to be negative. So my epsilon parallel becomes negative. And if epsilon parallel becomes negative, then this becomes the equation of a hyperbola, right? And you get an equation of a hyperbola whenever you have this negative sign coming in. So metals with epsilon below 0 show this property, and you get this hyperbolic dispersion inside this material. What this means is that for light, when these layers are really thin, perpendicular to the layers, it acts like a dielectric, and parallel to the layers, it acts like a metal. And we'll see what this means to density of states. Well, to understand this, we should ask the question, well, at certain wavelength ranges, this material is going to have an elliptical dispersion, because remember, metal has this epsilon going to negative only at certain frequencies. So below that, it should be all positive, which means it should be elliptical. But then at some wavelength range, it becomes hyperbolic. So you're going from an elliptical dispersion to hyperbolic dispersion, which means you have to go through a singularity to go from the elliptical to hyperbolic topologies. So where is that coming about? Well, we weren't the first ones to think about it. Lifshitz had thought about this in the 60s in the context of what is called Lifshitz transition for Fermi surfaces, where the Fermi surface goes from a closed topology to an open topology, and then the magnetotransport goes through these singularities and so on. So he had discussed this. What we realized is the isofrequency surface can be mapped on to the Fermi surface that we talk about in the context of condensed matter. And now the optical density of states has to go through a singularity inside the system. And which means if I now, and the reason is, and one naive way of thinking about it is, if I start counting the number of states inside this system, this is your textbook picture of how you get the density of states. And the density of states is always counted, but the density of states is limited by the maximum wave vector you can have inside the system. But if you look at this hyperbolic scenario, where it's an unbound system, you don't have a limit on the maximum wave vector you can excite inside the system. Of course, from a practical standpoint, the limitation comes because you have remember, all of this is based on an effective medium approximation, and which means the layer thicknesses have to be comparable or much smaller than the wavelength of light. So the large k vectors means the wavelength is shrunk, will become comparable, and then this approximation fails. So it will work till a certain value. So the basic idea is that you have an open system, you get an increase in the density of states, and that should give rise. So Fermi golden rule, you're playing around with the density of states, you should get something similar to what you see in cavities, which is your increase in spontaneous emission rate. So we've done this work. The first paper that we did on this was in 2012, where we looked at this transition, showed that there was increase in density of states. But we realized that these 2D materials are a nice platform to study this, simply because when you place an exciton on, or these 2D materials on top of this hyperbolic, you're sitting in the near field of this material. So one of the requirements is that these excitons, or whatever is the emitter that you're using, has to sit in the near field of this hyperbolic medium, because only then it couples to the system. So so this is what we did. The first experiment that we wanted to do was this. But if you look at the simulations, what you see right away is you have your emitter sitting here, and most of the light is trapped inside. So to understand that, let's think about this. You have this hyperbolic dispersion, and you're exciting these really large wave vector states. And when you excite the large wave vector states, all of these states are lying below the light line. So there's no way you can actually access these modes. It's unlike a cavity. These modes are sitting all below the light line, and there is no way to access them because this is your light line here. So in fact, this is a simulation just showing what happens if I just shine white light onto this sample. Everything is going to get reflected back. Nothing is going to couple into the system because there is no high K states you're exciting. However, if you defined a lattice on top of this, and the lattice doesn't have to go through all the way, so it's just a photonic crystal structure that you're defining on it, you fold all the modes above the light line, and now you can couple the light into the system. And it's exactly what we see. So you see that there is a lot more light that is getting coupled inside. So a lot more details on exactly how this structure works is in our recent PNAS paper, where we show that you can increase both outcoupling. So one of the big criticisms of hyperbolic medium was, okay, so you can increase your spontaneous emission, but what's the big deal? You can't get the light out. So, and the biggest Purcell enhancement is happening inside the material. And if you can't get the light out, what's the point in doing Purcell enhancement to begin with? But what we show is that if you actually have an array of a lattice here, and if you design the lattice appropriately, you can actually get both increase in spontaneous emission rate and outcoupling can also be enhanced from the system. So we went ahead and did the experiment. So this is our structure. This is the scanning electron microscope image of the lattice, 2D lattice that was defined. And if you can see very faintly, there is a triangle sitting here on top of this, and the triangle is the 2D material, and it's covering a whole bunch of these structures. And one of them is designed to the right wavelength, and you see that one showing up as most brightest, and you get a certain increase in the intensity. In fact, this picture shows it much more clearer. So this is a scanning confocal image where you see that most of the emission is actually coming from where the hypercrystal is sitting. Or we call it the hypercrystal because it's a hyperbolic medium with a photonic crystal, and my theory collaborator decided to call it a hypercrystal. So nevertheless, you do get a large increase in intensity of emission from both in terms of rate, which is shown here. So you get the spontaneous emission rate to go down, to speed up, and also get an increase in the light output from these materials. So in the last 5 minutes of my talk, I'm going to discuss our most recent work on quantum emitters in boron nitride. So everything else I talked about right now was on transition metal Di-Chalcogenides, where we've got strong coupling and another approach towards modifying the spontaneous emission rate. Most recently, we've started looking at boron nitride as a way to get single photon emission. This is work with my colleague Carlos Merles, and who works on diamond, and who's told me about all the problems with diamond. And the simplest one being that it's hard to process it into any kind of photonic structures, or you need to, you can do it, but it's not that easy. So in 2015, there was a paper in, which showed that boron nitride actually has defects and you can get single photon emission out of it. We did some experiments following up on that, where we looked at the role of the emission intensity, emission wavelength, and how it can modify. And the reason I put up this slide is for two reasons. One, you do get the anti-bunching out of these defects, so it's you're getting a single photon emission. But you also see something else here, which is that it's the same sample. I'm looking at different regions in the same sample, and I can get single photon emission, which can vary anywhere from 550 nanometers to close to 700 nanometers. So I have no control over what wavelength this thing is going to emit. Well, you can twist it and make it positive, saying that I have wide tunability, but from my standpoint, it is, you have a system where you have no control over what wavelength is emitting in the sample, and so that's not good. Second, you have no control over where it is going to emit. So, and the third problem is there is a lot of spectral diffusion. Some samples do not show, some emitters do not show spectral diffusion. So this is over a time scale of about 280 seconds, whereas in this case, they start showing some of the jumps, and in some scenarios, you actually go between multiple jumps. So in my opinion, this is a real problem. If you really want to do this properly, then we have to first control the wavelength, be able to control some of the spectral diffusion, and also be able to possibly place it at the right place. So this was our first paper on this. And what we've recently managed to do is the following. So this is a nanopillars of silicon dioxide, and we have encapsulated it with boron nitride. Now, a similar approach has been used in TMDs, but in TMDs, the physics is different, because what happens there is you have bound excitons. Here, you do not, just to remind you, HBN has a band gap of 6 eV. So these are not bound excitons that you're creating. These are defect states inside this material. So what we do is that we put this TMD material on top of this HBN on top of it. These are about, it's not a monolayer, it's about 20 nanometers thick, but it folds like a tablecloth around these pillars. And this is an AFM image that shows 1 layer, 2 layer, and 0 layers, and we can look at the emission pattern that's coming. What you see here is every array point is actually emitting light, and you get, so this is a confocal image that shows, and you see a one-to-one correspondence between an optical microscope image and the confocal microscope image. So you're getting light emission at all of these pillars, and the light emission spectrum looks as follows. So you have a main peak, and then you get the phonon replicas, which are about 165 millielectron volt, separated from the main peak, and you get multiple of these replicas. So that's the spectrum shown here. You can look at the lifetime. It's got about 2.45 nanosecond lifetime, and it also shows the anti-bunching. So we're convinced that we are at a point where each of these sites actually has 1 or 2 emitters, at least in this particular case, we are down to about 2 emitters at this particular site. We need to work better to get it down to 1, but that's one aspect. So we were able to control where the emitter is coming about. The second thing that we were able to do was actually suppress the emission wavelength as well. So instead of this whole distribution that I showed in the first work of ours, where we were getting from anywhere from 550 to 700, right now the emission is centered around 570 nanometers with a reasonable full width half maximum. And also this is the time trace, again indicative that we actually have a single quantum emitter inside these systems. And we've gone ahead, and so this is the AFM image. And then actually, if you zoom into one of these at the pillar, what you see is that most of the emission is not, it's not coming as if it's emitting from the pillar. Most of the emission is actually coming from along the edge, where actually the defects are getting activated due to strain. So we are not inducing defects. On the other hand, what we are doing is there are already defects in these materials. We are activating them through strain in this system. So with that, I conclude. So the work we've done, we've shown the microcavity polaritons, the helicity in these systems, spontaneous emission using this photonic hypercrystal idea, and some recent work on room temperature single photon emission. I'd like to acknowledge all my collaborators, students who made it all possible, and I'll leave it with this and we'll be happy to answer any questions.
Questions?
Very, very nice, impressive. Is it known in boron nitride what these defects are? Are they single vacancies or?
So there is both. There are people who talk about this as being a boron vacancy or a boron substituted vacancy, and no one knows the answer to the. At least I haven't seen anyone saying it with confidence what it is. There's a lot of EPR work from the 70s on these systems. So the other aspect I should mention is, unlike diamond, we have not seen any magnetic field response. We have tried it, we have not seen anything, and not so have in most of the other groups. So yeah, we don't know what kind of defect it is. Yes. Yes, these are, so you have to start with a material that is already bad with a lot of defects. So we buy it from a company called Graphene Supermarket. So that should give you an idea of how bad the materials can be. And so these are boron. So if you get the boron nitride from the famous Japanese group, then you don't see these emitters.
Irradiation?
Yes.
Or?
So there is. So the original paper that I showed was from Igor Aronovich's group in Sydney, and they have actually done some electron irradiation and tried to do it. Dirk England's group has also tried to do something along those lines with ion implantation. That's another approach that one can take. What we have done is, so the other way to do this is you can just take this material and anneal it at 850 Celsius, and that activates the color centers. But again, you don't know where they are going to happen.
More questions? Okay, so if not, let's thank Vinod.